Well, howdy, physics sleuths and inquisitive souls. Welcome again to Dynamic Gravity. So, in this episode, we are going to dig deep. We're going to dig very deep. Primarily so that we may bury a foe. So, before we bury this theory, we should first do a eulogy and kind of explain why we had to kill them in the first place. And of course, that is death to the Big Bang Theory. I think by the time I get done with this, you are not only going to know why the Big Bang sucks and is full of crap, but you're also going to know my alternate theory on how the universe began, something that I created about 8 years ago, maybe 9 years ago now. I don't know. I lost count of these things. Once I developed my theory of gravity, I realized that it was completely incompatible with the Big Bang Theory. Most people would probably just assume they're wrong and everyone else on the planet is right. Not this guy. Nope. Not me. So, on that note, let's dig into it. And before we do, I just want everybody to know that's new to this channel or has not yet. As with all my videos, I post in the description a link to view a short paper describing how dynamic gravity works on a subatomic level, how everything works, how it explains time dilation, how I developed the math, how I use it to calculate all dark energy and dark matter throughout the known universe. It's all there. I recommend you take a look at it because I ain't full of shit like other people. So, let's dig in. Alrighty. I mean, a lot of waves recently made. The James Webb Space Telescope has, discovered some things that a lot of people in cosmology did not expect to ever be discovered. Primarily, it is seeing galaxies that are redshifted, meaning they're really far away from what we can tell of how light works. So far away, and they're so old because the light travels at the speed of light. So if they're like 14 billion light years away, then we know that they had to have been at least 14 billion years old. And here's some redshifts they're seeing, like 10.39, 11.58, 12.63, 13.20. Ouch. Ow. Keep in mind, I don't know exactly how old they say the universe is, but I think it's like around 13.5 billion years old, something like that. So a lot of these galaxies, man, they're legit only like 300 million years old. And some of them, they think are up to 10 times the size of the Milky Way. And that's just not possible. You know, if your Big Bang occurred, like everyone says, 13.5 billion years ago, and we can go back with the James Webb Telescope now to like almost that time, and we can see, hey man, from the time, like literally as soon as you said the universe went bang, just 100 million years later, there's these huge galaxies, 10 times the size of our galaxy, already formed with a black hole, supermassive black hole in the center holding all together and everything. And there's just absolutely no known mechanism that this can happen. All right. So they don't want to give up on the Big Bang yet because they want to try and salvage it. Instead, they're saying, well, maybe we just don't understand galaxy formation. Yeah, maybe that's the problem. Yeah, guys, I'm sure that's the problem. I'm sure that's what it is. It has nothing to do with the fact that you have no clue what gravity is or how it works. But here we go. Here's a thing. Earliest known galaxies. James captured image spectra of 4 extremely distant galaxies. Their light was emitted less than 500 million years after the Big Bang. You know, I mean, here we go. Look at this. 325 million years after the Big Bang. And look at this. You know, that's a whole galaxy, dude. 346 million years. A redshift. My God, just look at that. 390 million years, 354 million years. Redshift that. This is insane. None of this works. So modern science is finally starting to catch up where I was at 10 years ago. Will it ever get to my level? Good luck. I'm pretty far ahead of the crew. But so we got and I think like 1920 something. When was it? Where was it? 1922. Discovered disagreement equations. That's not quite. I think it was like 1928. Maybe 1927. Anyways, they did some looking out with telescopes, and they figured some stuff out, and they're like, hey, dude, the galaxy is expanding. And everything, the further away it is, the faster it is going away from us. So the entire galaxy is expanding outward, as much as it can, everywhere it can find. It's expanding outward. And so Hubble, Edward Hubble discovered this, and, he gets credit for this. Well, we named a nice, beautiful telescope after this man. And then George Lemaitre, I don't know, some dude comes along, and he's like a Catholic priest, man. I mean, I guess he's an astronomer too, but as you see, here's a picture of him. He's got his little priest thing here, man. He's a priest. He says, yeah, your whole science thing is cool, brah, but what if I just said God did it? Can you prove me wrong? So the evidence was, okay, the universe is expanding out. And so this guy comes along, George Lemaitre, and says God did it. It all started from God snapping his fingers and saying, let there be light. And then poof, the entire universe came into existence, and just it didn't like how close proximity was, so it expanded out in a massive explosion unlike anything ever seen. And yep, that's how the Big Bang Theory. That is essentially the Big Bang Theory. Prove me wrong. And it's like, okay, dude, I get it. I mean, hey, I'm a believer in God myself, but I don't think that's how it all started, personally. But he did a good job. He snuck God into religion a long time ago. Everybody bought into it, and it's very interesting. Certainly, I do appear for scientific form, 1931. In a paper, a Belgian cosmologist and Catholic priest, the theory, accepted by nearly all astronomers today, was a radical departure from scientific orthodoxy in the 1930s. So I guess it took a while for people to get aboard on this, but they did, and that's the thing. That's essentially how the Big Bang became a thing, and that's why it's been the most relevant and successful theory it has become, because everybody wants to do with Einstein's general relativity. Well, guess what? There is no mechanism in general relativity for anti-gravity. It doesn't exist. It's impossible. So you have to have some huge, massive amount of force directing the entire universe to expand, going against the force of gravity. And so everybody said the Big Bang, God, an explosion, poof, let there be light. But there's problems with that. Number one, we see that the expansion of the universe in recent decades is accelerating, not decelerating, like you would expect if it were to be, as they said, an explosion, a singular explosion that God created, and then after that, gravity takes effect. So there's a lot of problems with this. It's dying. It's every thing we see as we get further and further along the edge of our science is only showing how wrong they were. But if you're wondering how my theory holds up, it explains everything. Everything. There's nothing left. It explains all observations. I have yet to find one I cannot explain with my theory of gravity. Everything. I'm just saying, it is what it is. So, moving along, we've got what is this? Yes. All going into the Big Bang Theory. They have all these things where, I don't know, after like 300,000 years, they guess magically. I say they guessed because it's like the Higgs boson, where they had all this math where they tried to predict everything according to the math rules that they're playing by, and the math was so far off. It was like a factor of like 50 or 100 or 1,000 off. And they just kept, saying, well, maybe it's this then, or maybe it's this, and mixing their math all around to try and fit the observation. And even doing that, they just keep failing. So they've revised this theory multiple times over the last 90 years. And, every time they make a huge observation, it just all falls apart. All their work just disappears into nothingness, the big void, because it's a wrong theory. I hate to break your heart, sunshine. It is what it is. So, yeah, they did. Here's NASA, saying limitations of the Big Bang Theory. That's their polite way of saying, yeah, this is problems that we have to figure out, but we don't know why. One is the flatness problem, and that's basically saying, if I'm not mistaken, they believe the universe has a minuscule curve to it somehow. And if this were true, then when the Big Bang began, if it started off with a little bit of curve, as it spread apart, there would be a lot more curve. But we don't see a lot more curve. We see virtually little to no curve. So this is a huge problem against the Big Bang Theory. There should be expected a lot more curvature in space-time if it were a thing. By the way, space-time is all bullshit. My theory of gravity is the one-all be-all. Read my paper if you don't get it. The second problem is the horizon problem, right? So if you look out at the Big Bang, everything is like the same temperature. I mean, it's like 1,000th of a degree off, but essentially the same temperature. There's no way this can happen if everything is expanding out at the speed of light or faster than the speed of light, because space-time is expanding or whatever. And so there's no way that it can communicate that we know of to exchange heat or values of any sort. So you would not expect it to be uniform, at all. And another thing is, let me look it up here. Yes. So because it is completely uniform, if a explosion or expansion of photons and matter occurred, we would not be able to observe it. No, that's something else different. Yes. So I'm trying to read my notes here. Basically, as it expands out, if it were all the same temperature, if it were all the same reading we're getting, it's all homogeneous or whatever, it's all the same from every direction we can measure to the umpteenth degree that we can measure mostly. There are only two ways that can happen is like they say, the horizon where it shares information, or if you're in the exact center of it all. Then as the explosion occurred outward, then yes, everywhere you looked out, you would expect to see more of a homogeneous effect. But that's kind of vain, don't you think, to think that in the whole universe that is so large that we don't even have a number to say how many stars are in it, and yet we are the center of the universe. I don't buy it, man. I don't buy it. And once again, it's heavily threading and interweaving God into science. And I'm a Christian myself. I'm many religions. I believe in God of all different faiths, but I do not believe that He created the universe in this manner or like this, or even did it altogether. It is what it is, and you can't make me believe that. Another problem is the monopole problem. According to their math that they have, and they did, there should be magnetic monopoles that are large and observable all over the place. Yet we've never seen one ever in the history of the world. So if there's so many, why can't we find one? if they're predicted to be everywhere, why can't we see just one anywhere in a laboratory, out in space, anywhere? It doesn't exist. So some other problems are all photons are equally redshifted. Yes, there's impossible to show the center Big Bang. Okay, that's what I wanted to explain. You can't have photons without atoms and electrons without protons. Yeah, without atoms and electrons and protons. So the soonest we could see the CMB radiation is after like 370,000 years after the ground zero, because there was no matter, as we know it, in the universe to create electromagnetic radiation. This is another problem of everything, which a lot of people haven't quite caught on to yet, but it is a thing. Also, if the expansion occurred, then they would not be able to observe it unless we were at the edge of the bubble. Okay, so yes, let's do this. Blah blah blah. Let's do this. This is an important concept. So you got a thing here, right? And you light it with a fuse, and pop, 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 and it explodes. Bah, 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 bah. Right. So you got all these little particles. What are these particles? Or photons, or actual bits of matter, or quarks or subs or whatever. They're going to go out at such and such rate. Okay, this is going to happen. Well, guess what? Let's say you're observing this whole reaction taking place from like right here, right? And we'll call this Earth, all right? So everything that's coming out, let's say it's photons, all right? Once it explodes, you're not going to see these photons ever again once they pass you. Like, it's going to start off a small bubble, and then it's going to get a bigger bubble and a bigger bubble. And once they pass you, that's when it's going to hit you, and you're going to register like, oh, crap, there was this huge explosion. It happened right around here. We saw it. But as these photons continue to go outward, as they go outward, that's it. They're done. They pass through you. If they're gone, you're never going to see them again. But according to the Big Bang, you do see them. They call this the CMB, the cosmological background. They say this is the remnants of the energy of the Big Bang they're looking at. They're saying this electromagnetic radiation is as old as the universe, and when it first started, it was gamma rays, and now it's been redshifted to photons. That's what they say. And it's like, dude, do you not understand how photons work? Once they go by you, pew, that's it. They're gone. You don't see them anymore. It doesn't work like that, all right? It amazes me how retarded some of these cosmologists are when it comes to basic principles of physics. But I digress. So yeah, let's go into the redshift a little bit. So the redshift they calculate of the Big Bang, they say it is 3,000. All right. And you're like, well, how is it 3,000? Well, because the CMB is 2.725 Kelvin. That's the temperature of that. And so what they do is they divide 3,000, which is the temperature they calculated with their math, Kelvin, at recombination, when all the matter came together and formed electrons and all this crap and atom. And when you do that math, it equals like 1,100, right? So they say that this is the redshift is 1,100 of the cosmological background. But as we have seen, the most redshifted objects in the universe that we see is only like 13.5, 13.2, whatever. So this is kind of a huge problem. All right. They're saying the redshift is like, I don't know, 100 times more than the most redshifted object we've ever seen. And this is all just math tricks, like how they used to discover the Higgs boson and all that stuff. And this does not even include how space-time has expanded over the last 13 billion years, and how the observable edge of our universe is not 13.5 billion years like you would expect, but actually closer, like 46, 47 billion years. This is insane. Like, I'm sorry, but this is what they used to prove the Big Bang Theory too. Think about that. This is why they're so smug about it. Well, obviously the Big Bang Theory. Don't you see the math? Yeah, I see it. I don't like it. It's all bullshit. So, yeah, like 13.2, 13.3 is like the most highly redshifted object we know of. Like, I think it's Galaxy HD1 or something. And it's a fraction of what they have to make the redshift of the Big Bang, right? Also, the Schwarzkopf metric, which best explains gravity using general relativity. It completely ignores the expansion of the universe. 100% doesn't account for it. So the only way for our theory of gravity, or Einstein's theory of gravity, to work is to pretend that there is no expansion of the universe. This is really getting ridiculous, okay? Let me see. What else we got here? There's no science to explain how all the matter in the universe was instantly made that violated the law of conservation. Law of conservation says you have either energy or matter. You can convert the two, but you can't make one or the other. They are what they are. You can convert, but you can't make. Well, the Big Bang Theory says, hold my beer, God snapped his finger, so there be light, and now all the matter in the universe violated the law of conservation and was just made instantly and put into place. This is crazy. Let me see. Is this all that I have for my notes, and we can finally start getting into my theory? Yeah, let me see. All photons are equally egg-shifted unless possible. Listen to the Big Bang Theory. Yeah. Okay. All right. So yeah, this is not all, but most of the problems for the Big Bang Theory, and why this is such an issue. So, one of their big proofs of the Big Bang Theory is the cosmological background, where, this is kind of the graph they've made of the universe all around us, where they look out all directions. And this is a very misleading graph. These temperature differences, what they're measuring as temperature differences, are like 1,000th of a degree. So in actuality, if you looked around like temperature as we would think of it as, this would be all one color. It would just be completely normalized. But they say they can look at these minute differences of 1,000th of a degree and claim that this validates the Big Bang Theory. Once again, just math they've created to prove what they want to prove. But in reality, when it comes to observation, it doesn't add up. None of this does. None of it does. So, yeah, that's the cosmological background. And I believe, if I'm not mistaken, it is like 2.25. Yeah. So almost everything is like 2.725 degrees. So all these are off by like 1,000th of a degree, right? But there's this thing in physics that we know called black body radiation. And what this is heat is a form of energy, right? Heat is essentially when an electron moves in the presence of a proton. It moves. And if it moves too much, it'll break away and start performing chemistry like fire. If it doesn't, it'll release energy in the form of heat like infrared radiation. And so the more you heat up something, the more photons or photonic energy it's going to release, like the higher wavelength of photons it's going to release all the other photons before it too. but it's going to release, keep going up and up as the hotter you get. And use a chart to explain that. So when you heat up metal, like lava, for instance, it gets red hot. Okay, now it's hot enough to emit infrared light. And that's why it looks red to us. It's that hot. And this goes on and on. This is, quite impressive. So the biggest proof for the Big Bang Theory, the CMB, they claim, I would say what they're actually measuring is matter. Just matter dispersed throughout the universe, probably more realistic just without our solar system, but without our galaxy, like dust or something, space dust. It's not going to be absolute zero because there's going to be photons transmitting energy throughout all of space and virtual photons too. And so it's not going to be absolute zero. It's going to have enough energy to hold itself together. Otherwise, if it goes to absolute zero, it's going to do what's called the Bose-Einstein condensate effect, right? Where the atom no longer has energy being put into it enough to hold itself together. Kind of the law of conservation, if you think about it in real time. This occurs the closer you get to absolute zero, the less energy it has to hold itself together. So atoms will merge into this plasma form where they all have the same wavelength, and you can't really tell matter any part. It's really weird. So what I believe is going on here is that it's just like space dust. It's just matter, hydrogen, whatever, in space. And I know they've measured hydrogen to release like a 21 centimeter wavelength when it flips its orientation or its spin, and they say, well, that's how we know where the hydrogen is. But, they don't know everything. So if you were to have a black body emission at, like, say, 2.725 degrees Kelvin, it would be very low energy emission. It wouldn't take a whole lot of energy. Just like photons, probably from light, would be able to heat it up that much from just stars thousands of light years away. It could probably easily do this. And so that's what we're seeing, I believe. When we look out at the when we look out into the starry night and measure the cosmic ray, like here's Earth, right? Earth. Boom. Earth. Right? And as we go out of the solar system, let's say this whole thing encompasses our entire galaxy. All right? There's going to be a lot of specks of just dust, dirt, and stuff all around us, everywhere you look, all around us. Hydrogen, helium, lithium, all these gases, man, all of it, just little clumps, right? And as we look out any direction, we're going to come across and we're going to hit multiple of these particles, okay? And we're going to see through radio telescopes that they do have enough energy to release 2.725 Kelvin worth of heat is where the temperature they're at, their black body emission, because that's how much energy they're getting from all the starlight that they're absorbing in. And so if you ask me, the CMB is nothing more than dust that we see in our entire galaxy, probably. I don't even think it's other galaxies. I think it's just our galaxy. But maybe it's other galaxies. I don't have all the answers, guys. All I know is that the people that tell you they have all the answers are full of shit. And I wouldn't believe a word they say. You're much better off believing everything I say. Trust me on that. I at least think about everything, not just one aspect. But so yeah, that to me is a good explanation of what the CMB is. All right. So if we go deeper into this, okay. Now you're asking, okay, dude, you've done a good job, or at least you put a lot of doubt in my mind that the Big Bang is not where it claims to be. It's wrong. So what's the answer? The answer is a theory that I call the gradual universe, okay? And it's because it didn't occur in a big bang. It occurred in a very slow buildup, okay? Now, matter has to somehow create itself, okay? We know that we can make heavier matter from lighter matter, like in fusion found in the sun. Here is a process of that proton chain fusion reaction. But that's not creating matter from nothing, all right? Let's say we're starting with a big void of space, empty, nothing, no matter. How do we get matter? All right. The Big Bang says that God just snapped his fingers and poof, it all just exploded into existence. I say it was probably more a quantum event. All right. The quantum foam. The quantum foam or space-time foam is a theoretical quantum fluctuation of space-time in very small scales due to quantum mechanics. The theory predicts at these small scales, particles of matter and antimatter consistently created and destroyed. These subatomic objects are called virtual photons. Made in 1955, all right? So we know the quantum foam is a real thing. We've measured it. It is real. And we know that particles can come into existence out of nothing from the quantum foam, these fields that permeate through everything, as long as they're destroyed immediately because they're creating matter and antimatter pairs that immediately react to go back into pure energy, into the quantum foam, which is just a form of energy spread across the universe somehow. We don't know how or why. We aren't there yet. Maybe in a couple hundred years we will be. But we know this happens. So, obviously, matter has to be created from the quantum foam. Okay? And when that happens, now you can have a bunch of other processes like fusion, but that only occurs under really high temperatures and pressures like you find in stars. So that's probably not going to be what's going to be creating the majority of our matter throughout the universe, like hydrogen gas, for instance. So let's dig deeper. God, we got to dig so deep on this one. I know we're killing the Big Bang Theory, guys. We have to dig deep. So we got a process called electron capture, okay? And what that is you will have like a little proton. It's surrounded by some neutrons, or not neutrons, electrons. And then it will get hungry. That proton is so hungry. It's so hungry. And it'll eat it. It'll just eat that proton. Gobble it up. Now, it only can do this on rare circumstances when it has extra energy because it has to somehow create an anti-electron because that's how matter is stored. You cannot have an electron engulfed in a proton unless there is an anti-electron canceling out the energy of the electron, now allowing the proton or the quarks to store it or capture it. So you get energy in of a stable system, you mess it up, and now you got electron capture. And so what happens if you have a proton that eats an electron? It now becomes a neutron. Right. A neutron. So a proton can go to a neutron with just some energy input as long as it's got electrons around it. And the vice versa can also occur, called beta decay, where you have am I got this one right? Yes. Beta particle, fast, energetic electron and positron emitted from electron nucleus, transform nuclide isobar, for example. Beta decays of a neutron and transforms into a proton by emission of an electron accompanied by an antineutrino. So, we know this. We can absolutely change protons into neutrons or neutrons into protons. So, we can up matter up. We know this. So as long as we start with hydrogen, we can turn that hydrogen into helium. This can happen. We can turn that helium into lithium. This can happen naturally just by simply adding energy into the system through either beta decay, turning neutrons into protons with electrons and positrons, or through electron capture, where a proton turns into a neutron. So, two interesting things, right? They can go back and forth as long as they have energy, either being emitted from them or absorbed by them. This is the secret. It's all about energy. You have to do this to go up or, whatever. So, let us dig deeper. So, we know how we can get a hydrogen to a higher level atom like helium or lithium. We don't need a Big Bang. This happens naturally as long as there's energy around. Now, we have the electromagnetic spectrum. This is the wavelengths of electromagnetic radiation emitted from electrons and protons in their vicinity as they're moving around doing things. Okay? There's some important things to realize here. Number one, look at the length of photons, okay? The photons are what's being emitted in electromagnetic radiation. It's the packet. So you got photons at wavelengths, meaning how long they are. And you can see they get pretty long. Like this is like 10 to the third for radio waves, like 30 feet or something. I don't know, it's a lot. Microwaves, infrared, get a little shorter, visible light, even shorter, all the way till gamma rays are the shortest on 10 to the negative 12th, which is like, I don't know what, 1.2 nanometers or something. It's very small. It's very small, right? But if you look at the energy, it goes downward or upward in a line. Not, oh God, sorry. I'm wasted. It is what it is. Not an exponential growth rate of energy, but in a linear. Linear is the word I'm looking for. So this is kind of telling me that, okay, we have a packet of energy, right? A packet of energy that we are calling a photon. Photon. Yeah, I can't write this. This is too bad. And it's the same energy. All photons kind of have the same energy. Now, you can have a radio wavelength photon, which is going to be very long, but it's the same energy. It all equals one photon. This equals one photon. It just takes a lot longer to hit you with that same energy. Or you can have a gamma ray where the energy is very small, still equivalent to one. What the difference is in the length of time that this one photon could hit you, you could have literally like 100 of these gamma ray photons or X-ray photons hit you. So now we say that a gamma ray or whatever has 100 times more energy than a radio wave photon, because in the same period of time that you would get one measurement of energy from the radio wave, you get 100 from the gamma wave. So we say a gamma wave is 100 times more energy, but it's not. It's not. It's the same energy. They both equal 1. The difference is one, the entire energy is hit on you over a period of, like, say, a second, where one, the entire energy is hit upon you over, say, 100th of a second. And then you can have 100 more photons hit you in that period of time, or being released or emitted in the same period of time. But photons are quantum devices, meaning they have a specific value. So a photon is equal to a photon. When you encapsulate, when you take into account its entire energy that is carried, it all kind of equals the same. That's what I get. Anyways, that's what I see when I look at this. Okay? So all photons are equal. They're just spread out over different periods of time is the difference. Now, you might be saying, that's really cool, brah. How does this create matter? Well, I want you to look at this. The highest photon energy that we have is a gamma ray right here, right? Gamma ray. Around 10 to the negative 12, whatever. Guess what? When they did quantum mechanics back in the day, they figured out the wavelength of what an electron would be. And they found out that it had to be, like, I don't know, this is some ridiculous website, but whatever, I'll take it. I don't know if these numbers are correct or not, but it's probably, I'm assuming it's better than what I could do guessing. So they say the wavelength of a basic photon and a hydrogen atom is going to be equivalent to pretty much the size of the hydrogen atom, because the wavelength of the electron is spread out through the entire atom. So this is going to come out to be about 10 to the negative 10th. All right, maybe a little more, whatever. So we know that if you get much smaller than this, actually this one right here, the way they have this listed, it's a little bit smaller than this number. Probably not accurate, but it is what it is. Basically, though, if you get a photon that is smaller or the same size, the wavelength is the same length as the wavelength of an electron, guess what you now have? An electron. And this is one of the reasons why if you go back and watch my video on virtual particles, I explain this into great depth. Virtual particles are photons, are virtual photons, and they're photons. And basically all photons are essentially a small bit, if not even an equivalent bit, of an electron. The amount of energy that an electron represents being shot out in a different form of energy that can be absorbed by other electrons. All right? So if you have a photon, which is essentially almost equivalent to the electrically energy of a electron being shot out, if it's spread out through time, it's not going to be an electron because it's going to release its energy too slowly. But once you shrink it to the size of, say, a gamma ray or smaller, Now, essentially, you've created energy in the form of a photon, electromagnetic radiation, but because it is such a small wavelength, it is shorter than the wavelength or the same wavelength of an electron, so now it becomes an electron. So we have now converted energy into mass. We have created energy or transformed energy from a photon or a virtual photon into mass, an electron. All right? Excuse me. Brain damage from the war. I apologize. I'm all jacked up. Let's dig deeper. Okay. So, we've got the Bohr radius of an atom is, I don't know, they say it's around this, depending on the atom, I guess. How many electrons, neutrons, everything it has in it, depends. But as you can see, coincidentally, it is in the same ballpark as a gamma ray. But if it gets to be smaller, it pretty much turns into matter, because a photon is a capsule, a quantized form of energy. And that's essentially what matter is. The shortest, most quantized short form of energy that you can get to where it consolidates into what we call matter that creates all the known universe. Okay, let us dig deeper. So, determining the electron structure, I'm not 100% why. Oh yeah, I think I looked at this one for the size of an electron. Unfortunately, I don't see it here. But this one went off basically to show you the size of an electron. And it's pretty small. There we go. They say there's different ways to get it. But classical value, I don't know, like 2.8 to the negative 15th, as you can see here. They say there's other ways, but if you use math, you actually come up with 9.1 to the negative 17th. My point is, there are no measured photons beyond gamma rays for energy. Because if it goes any higher than a gamma ray, it turns into an electron. All right, that's the important part you need to know. There are no photons more powerful than a gamma ray, unless you want to call an electron a photon, which is essentially kind of what it is. All right, so we now have a way to create electrons from nothing more than pure energy. And we have a way to turn hydrogen atoms into helium and lithium atoms to keep going up and up as long as there's energy being provided. So the core synopsis is we need energy to create the universe from scratch. And you're saying, well, there's one part missing, though. We got electrons, but we don't have quarks, up quarks, to make protons. Well, guess what? This is a Feynman diagram. This is basically a electron and an anti-electron that are colliding here. I don't know why both arrows don't go this direction. I think Feynman's an idiot for that personally. This is so counterintuitive and confusing, but let's pretend. Let's just pretend. So it goes into here, and then it creates gamma waves. All right. Now you need two gamma waves to create two electrons. So if you're going to have an electron and an anti-electron, you need two gamma waves to collide to do that with that energy. And yes, photons can collide. I know you've been lied to your whole life, and you say, well, they told me photons don't ever collide. They're not mass, and blah, 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 blah. All lies. It's just apparently their odds of colliding go way down the longer wavelength of the photon it is. So the shorter the wavelength, the more energy it has, like say a gamma ray, the odds of two gamma rays colliding are infinitesimally much higher than say two radio waves colliding. It is what it is. But let's say you get an electron and an anti-electron colliding, and then they create gamma waves, or more than gamma waves, technically. And then what they can create, one of the many reactions can come out of this interaction, is a quark, an up quark, and an anti-up quark, which will immediately emit a gluon, which holds two quarks together. So quarks, as far as we've ever seen in the Large Hadron Collider and Fermi and all this, they always are in pairs. Quarks don't like to be alone. They're very codependent things. So we know that from energy, from gamma waves, we can create quarks and antiquarks and gluons to hold those quarks together, which could possibly explain why the universe, even though quarks and antiquarks are made at the same rate, why we see quarks dominate the universe and not antimatter, because the antimatter, for whatever reason, emits gluons as soon as it's created, which gives the quarks the energy they need to bind together with other quarks that might also be undergoing this very same process, while antimatter does not have that luxury. Now, what happens to the antimatter, you ask? I don't know, but I'm pretty sure it's got something to do with the fact that it's going to get converted back into energy, which will then get transformed into another quark-antiquark pair with the gluon. And then now you have a proposed mechanism that can create all of matter throughout the entire universe without the need for God did it by snapping his fingers and said, let there be light. We have all the tools we need to explain the origins of the universe, but for whatever reason, people don't want to think of it like this. Now, if I'm right, if the universe was created through these such mechanisms or other ones that I haven't even described yet, maybe we don't even know about them yet, that's entirely possible, then we are not good, because dynamic gravity, if you have enough mass that conjugates together, you get celestial bodies. You get celestial bodies that start interacting with each other and crashing each other. Now you get super celestials, like black holes, supermassive black holes. And with supermassive black holes, now you have a proposed mechanism, if you look at my other videos, for the expansion of the universe. Dynamic gravity clearly states black holes are the sole cause of dark energy and dark matter. It is what it is. So, yes, I think we have explained everything. We probably should go into the Standard Model a little bit. We know this is pretty accurate, except for this Higgs boson particle here. We're a little suspectable, a little sus about. I'm not going to say it doesn't exist. I'm just going to say that their reasoning for why it exists is kind of weak sauce. That's all I'm going to say. And I don't think we need it going by how dynamic gravity works. But if you notice, a photon has no charge, but an electron does. That is very interesting. If a photon, as I claim, is also similar or related to an electron. We know they emit each other. We know one can turn into the other. But one thing that is very interesting is that they both have spin. And spin, the property of spin, basically kind of means whether it gets pulled or pushed in a magnetic field. Yeah. So we have a photon, which is being affected, even though it's not really affected by a magnetic field, as we can tell, although in reality it probably is. It's just to such a small degree we can't measure it yet. It's pretty crazy when you start thinking about how all these particles are linked together. And when you look at the decays of all these particles, like this top particle will decay into like a charm with an up, with all sorts of things. They all decay into like basically the tau is the heaviest version of the electron. So the electron is the smallest, most elementary version that can turn into the tau or the muon if it has energy. And here's the energy levels it needs to achieve to turn into that, as you can see. So for my theory, the gradual universe on how the universe expands to be correct, basically, there has to be a proposed mechanism of how mass can be created from energy, which we have. This is all well done and researched and scientifically proved. The problem is, with my theory, is that there has to be energy pervading throughout the universe. I mean, as the law of conservation says, you can have energy or you can have mass. And you can turn the two interchangeably to whichever one you want as long as you have one or the other. But you cannot create one from the other. So this is the limitations of my theory. I don't understand personally yet where the energy came from to convert into mass, like electrons, and up quarks to make protons, and then the matter that we know, and then hydrogen gas, and then celestial bodies, and then super celestials, and galaxies, and all this, and on and on and on. But I will say this, it probably has a lot to do with the quantum foam. We know that energy can be borrowed from the quantum foam as long as it's returned quickly. Well, maybe there is some process that we don't yet know of or not yet observed where energy is borrowed and there is an interruption in that process that makes it so that energy is never given back and it's just now becomes mass. That's what I believe, but I am not a particle physicist and I don't have access to their work, so I can't hash out the minute details and the finesse out the details of this whole theory of gravity, or not gravity, but the origins of the universe that I have. This has been a really long video. I knew it was going to be, and I knew it was going to break your heart, and I'm so sorry for that, but it is what it is. You want to fly with the gods, you got to put in your time. So I think that pretty much sums up the vast overall encompassing everything of my theory of the gradual universe on how everything came to be, and why the Big Bang Theory is completely garbage and wrong. I don't have all the answers. I'm not going to lie to you. I'm not going to bullshit you. I don't have a fully fledged worked out pathway system on how everything occurred, but I assure you it exists, or we would not be here right now. And I do believe that my theory of how the universe occurred is accurate, is 100% accurate. But eventually, time will tell. 1,000 years from now, let's see what they say. So, with that in mind, I wish you, farewell, good riddance, and good luck. Or good luck and good riddance. And I will see you on the flip side in a couple weeks. I'm going to take a break after this long episode and recoup. think about it and let me know what you think. Post in the comments. I love to hear what people's ideals are. I don't believe I know everything, but I do believe I know a lot more than you think I do. So with that, farewell, adios, my friends. I'll see you on the flip side. Goodbye.
Like, subscribe, submit.